Yes, thank you very much. So yeah, I'm Hiroshi Ohno from University of Tsukuba, and so maybe good morning or hello or good afternoon. So first of all, I would like to thank the organizers to give me an opportunity to give a talk here in this nice workshop. And today I'm gonna talk about some recent progress on the lattice studies of invariant properties of heavy quarks. And so this is the outline of my talk. And so first I will start with some brief introduction on this heavy quark on the lattice, and then I will show some lattice result on the heavy quarks at final temperature, especially for some spectral functions by using some Bayesian analysis, and also I will show some result from my collaborators, some studies with my collaborators on some heavy quark diffusion coefficients, and also some modeling of the spectral function by using some phenomenological knowledge. And then finally, I will summarize my talk. And first of all, so what is a heavy flavor? So as you know, so heavy flavor is basically a charm and bottom here. And so here, so quark-near, so which is Q-cube pairs, I mean Q-cube heavy quark pairs, and also open heavy flavors, which is heavy Q and light Q bar, or heavy light Q or heavy Q bar pairs are important probes to investigate quark-gluon plasma, which is formed in heavy ion collisions. Since these quark-near or open heavy flavors should be produced in the early stage of the collisions, which means these quantities, these quark-near or open heavy flavors should know something about some entire evolution of the QGP, and also that means one can extract some information from these quark-near or open heavy flavors. And also, these quantities are very important as a signal of the QGP formation, because after QGP formation, there should be some color device screening, and due to this color device screening, this quark-gluon production should be suppressed. So this suppression of quark-gluon production is a good, important signal of QGP formation. And also, some it has also already observed that some there should be some sequential suppression of the quark-gluon production. That's very interesting, because this means that this corresponds to a defined binding energy of defined bound state, and that gives us some information about melting temperature, and that is good. By using that, one can know which temperature is in some hot medium, and so by using these quark-gluon and open heavy flavors, what we can understand is, so basically, so here, so I show, as I said, there has been already observed some sequential suppression has been observed, and this is typical evolution suppression. And to understand this kind of experimental result, it is very important to know dissociation temperatures of heavy quark-gluon. And also, it is very important to know some hydrodynamic or transport properties of quark-gluon plasma to explain the experimental result. So, in some people try to understand the experimental result by using some sort of transport models. And for these models, it is some heavy quark diffusion coefficients or something, some transport coefficients are very important inputs for these models. So to understand these point of dissociation temperature and heavy Quark diffusion coefficients, it is very important to know the invariant properties of open or hidden heavy flavors. And the basically these properties are all encoded in the spectral function, especially in for the coordinate spectral functions. So it is very important to understand the invariant properties of these spectral functions. And next, I will explain what is a spectral function. And basically, so as I'm studying the lattice QCD, so here I will consider some Euclidean mesonic correlation function, which one can calculate on the lattice. And basically, so mesonic Euclidean correlation function is defined like this, and basically spectral function is hidden in this Euclidean correlation function like this. And so here I show some schematic picture of the temperature dependence of the spectral function, which we may expect. And so at very, at some temperature below the critical temperature, one should find some sharp, clear bound state peaks, like this ground state peak or excited peak, like this. And also, at very high frequency region, maybe one also should find some quantum structure like this. And if you go to further higher temperature, above crystal temperature, then maybe one also should find that this, some bound state peaks start getting broadened, and also maybe one can also find some peak should disappear, or maybe it is difficult to distinguish from some bulk structure that correspond to the melting of the bound state. And especially for transport peak, especially for some vector channel, maybe one can also find a transport peak like this, around zero frequency. This is a very important quantity to understand heavy Quark diffusion coefficient, because one can calculate heavy Quark diffusion coefficient from this from the behavior of the spectral function around zero frequency, like this. And if you go further higher temperature, then maybe this spectral function end up with the free case, and then there are no longer any bound state peaks, and also maybe you can only find some quantum structure and some sharp zero mode peak like this. And so maybe here then what I want to know is this kind of temporary dependence of spectral function, but there is some problem. So there are some many difficulties on the lattice to calculate spectral function, especially for this heavy Quark spectral function, because this heavy Quark mass is too heavy to put on the lattice, because since this Quark mass is very heavy, it is very important to have very fine and large lattices to control the lattice artifact, which needs very large computing resources. And also this is a very difficult problem, but obtaining spectral function is very tough, because this is known as famous impulse problem. Because as I said, this spectral function is hidden in this Euclidean correlation function, and what we can only calculate on the lattice is this Euclidean correlation function itself. So one needs to solve some kind of inverse problem. But on the, unfortunately, what we can get from the lattice simulation is some limited number of correlated data and correlation limited number of data points of the correlation function. But to express this good functional form of the spectral function, one needs more much larger number of frequency points. So in that sense, it is very, this is a quite typical ill-posed problem, inverse problem, and that means usual kind of simple I-square fitting does work, because there are many possible spectra within statistical uncertainties. So one can get quite noisy or maybe some spiky spectral function, if you just apply some simple chi-square fitting. And then, but there are some techniques to overcome these difficulties, and so to overcome this heavy quark mass, to overcome this the problem is that this heavy quark mass is too heavy. One can introduce some sort of effective field theory, for example, non-relativistic QCD or NRQCD in short, and also potential NRQCD or PNRQCD. Because this heavy quark mass is very heavy compared to the typical QCD scale. One can there should be some separation of scale, and one can do some sort of effective field theory like this. And also one can apply some sort of other techniques to extract spectral function, which is basically based on Bayesian inference. And in this kind of method, maybe one can add some knowledge which you have already known for the spectral function. And maybe the most commonly used method for this kind is so-called maximum entropy method, or MM in short. Or maybe nowadays, recently, there is also some new kind of Bayesian method called Bayesian reconstruction method, or BR method, and also there are many other similar methods. And also maybe one can not only directly extracting the spectral function itself, but also one can try to model the spectral function by using some knowledge based on phenomenology or some perturbative technique. And also, of course, maybe one can also approach this, tackle this problem by using some approaches without directly measure spectral function itself. And so here I will briefly explain what is Bayesian inference, or Bayesian method in the sense of the extracting the spectral functions. And here, so basically this method is based on the Bayes theorem, and here this PAAG means that some possibility to get some sort of spectral image behind some given correlation function data. And this is according to the Bayes theorem, this probability is can be written like this and this P, some product of PGA and PA. And so this denominator P of G is just a normalization. And here this P of A is proportional to some exponential alpha S, and this S contains some prior equation, and this is so-called prior probability. And also this PGA is a probability to get some correlation function behind some given spectral image. That means this is the usual likelihood function. I mean, this corresponds to usual high-square term. So this method eventually get this kind of form, and this F is the combination of this prior probability and the likelihood function. And so what we want to do is just get the the most probable spectral image, which corresponds to the maximum probability of PAG, and which also corresponds to the minimum of this F. So what one should do is just find to find this minimum of this F. And there are some different types of I mean sort of this S to introduce prior probability. And the most commonly used type is this Shannon-James entropy, which corresponds to maximum entropy method. And this Shannon-James entropy is given by this form. And so recently, some another type of entropy is introduced like this. And maybe if you have a good quality of you have some data which has a good quality, then maybe there should not be any difference between these two. But usually our data quality is not so good enough, so maybe there should be some sort of difference between the different methods. So that gives you some hint to get some systematic uncertainty. So it is very important to check, cross-check, your spectral function by using a different type of method and check the uncertainty. And here I also briefly show some another type of method, which is stochastic method. This is also some kind of Bayesian type analysis. And so basically, we try to use this stochastic method for our calculation, and we test it in this method. And this is our this is our result by using this stochastic method. And this left-hand side panel shows the conventional maximum entropy method result, and the right-hand side panel shows this newly introduced stochastic method. And basically, and these two plots shows the vector spectral function, charmonium vector spectral, which corresponds to J psi channel at 0.75 TC. And so basically, these two methods give more or less the same, consistent results. But however, there's also some some sort of difference between these two. So maybe it is good to check. Good to check this some uncertainty of this spectral function by using these two different results. Anyway, and then here we show some progress of this kind of spectral extraction of the spectral function from the lattice QCD calculations. And so here I summarize some lattice studies on the co-economic spectral functions so far. And so unfortunately, there are many different results from different groups, and these results are sometimes not consistent with each other. And here, for example, this is one example of example result correspond to Charmonium spectral function. And so basically, this result shows that this J psi seems to survive up to 1.5 TC. But some result, some group also showed that J psi already J psi is already melted much below temperature at some temperature below this temperature. Also, there are some studies correspond to the PVF channels, but also PVF channel result is also not still not conclusive. And there are also some bottoming results, and basically, since bottoming is very heavy, so basically, these people usually use some sort of effective theory, so-called NRQCD, and there are some results from different groups, but so basically, what they showed is that epsilon 1s channel seems to survive at least up to 2 times critical temperature. But for the P-wave channel, there are some different conclusions from different groups. So still, this P-wave channel is still not conclusive. So that's, and also, since this is NRQC result, so it is also good to cross-check these results by using by not using NRQCD. And so here I will show some recent updates on this type of studies. So especially, I will show some results shown in the Lattice conference last year, and so here I will show some results from so-called first-sum collaboration, and they basically now use full QCD calculation by using NRQCD. And here I show some epsilon spectral functions here. Basically, this left-hand side panel is just zooming out of this right-hand side, some frequency region of the right-hand side panel. And what they now they also have 2 different pion masses, and but what they found is that there is quite small or basically no effect of this pion mass dependence. And also they conclude that this epsilon 1s channel may survive up to some the highest temperature is 1.5 TC, 1.9 TC. And also the same group also showed updated some Charmonium result by using full QCD configuration. And here is the eta C spectral function, which is a pseudo-scalar Charmonium. And this left-hand side plot is spectral function from correlation, ordinary correlation function. And this right-hand side plot shows the spectral function from so-called the reconstructed correlator. And the reconstructed correlator is given by some different correlation function. Correlation function at different temperature, and basically they use some. That means one can check the dependence of the okay, and they change the temperature by changing the lattice temporal lattice extent. So in that sense, different temperature has different lattice extent. That means different temperature has different number of data points. So basically, one can check the number of data points dependence by by comparing these two results. And what they said is that they found some temperature dependence of the spectral function, but this temperature dependence was found both in these two different correlation functions. That means this temperature dependence might be due to the data point dependence. So that doesn't necessarily mean that this is the real temperature dependence. So then they conclude that they cannot still find any similar of the melting of this delta C channel. And also they did same analysis for J psi channel, and they also found similar behavior, and they concluded that they didn't find any melting behavior of J psi. But on the other hand, they also did same analysis for the open charm system, basically for open charm pseudoscalar channel here. And but in this case, they found that some really thermal thermal modification in this spectral function, and then conclude that this open charm meson can be melted already below TC. Okay, and so this is the situation of the reconstruction of spectral function itself so far. And next, I want to shift to some different topic, and from here I want to show some result of the heavy quark momentum diffusion coefficient given by our given by us. Some study with my collaborators, and basically for this study we use some quench QC deconfiguration, but this quench configuration is generated on very large lattice, which allows us, and large lattice, and we also have different cutoff offs. So that allows us to carry out some reliable continuum extrapolation. So basically, this is kind of first result for the quench QCD calculation by using continuum extrapolated correlation function. And here, what we have, we calculated is so-called color electric correlation function, which corresponds to the some static heavy quark system. So here, that means this system has infinitely heavy quark, and from this color electric correlator, one can also calculate some sort of spectral function, and from this spectral function, one can define Heavycock, so-called Heavycock momentum diffusion coefficient from its behavior around zero frequency. And here we, instead of using a maximum entropy method, we directly extract the spectral function itself. We tried to model the spectral function by using some knowledge of the path dimensional theory or something. And here is our model spectral function. And for the IR part, that corresponds to the very small frequency region. Essentially, we should have this kind of asymptotic behavior. So we simply define our IR part like this. And also we think about the UV part, and thanks to the asymptotic freedom, one can calculate the UV part from the path dimensional theory. And basically in this study, we use two different ansatz for this UV part. And finally, we did some interpolations, for this, within this IR part and UV part. And we eventually use these three different type of spectral function, model spectral functions like this. And by using these models, we fit our continuum extrapolated correlation function data. And so in this left-hand side panel shows our continuum extrapolated lattice spectral lattice correlation function as this diamond symbols. And this dashed line, each dashed line corresponds to our correlation function calculated from our model spectral function. And as you can see, our model can be can be fitted, to our lattice data pretty well, and corresponding spectral function itself are shown in this middle panel, and you can see some intercept here, and from this intercept, one can calculate the Heavycock momentum diffusion coefficient. And this right-hand side panel shows our resulting Heavycock momentum diffusion coefficient for a variety of our models like this. And from these models, we can get the Heavycock momentum diffusion coefficient, and also one can translate it to the Heavycock diffusion coefficient itself like this, and we get the value like this 2 pi times temperature times this diffusion coefficient is equal to something like 3.727. And then we compared our result to some other lattice QCD data, and basically this lattice QCD calculation is corresponds to the direct calculation of the spectral function. I mean, they directly extracted the spectral function itself by using a maximum entropy method, and they get the Heavycock diffusion coefficient like this, and for each temperature. And basically, this T2 pi times TD is around 2 for at any temperature. And so since our result is slightly larger than this one, but order of magnitude is quite similar. And also, very recently, there are some updated study has been updated study appeared in the archive, and unfortunately, I'm no longer in the member of this study, but some my collaborator continued to study this kind of calculation, and they updated our old study by using the gradient flow. Basically, they improved the signal of correlation function data by using gradient flow method. And then they get this kind of correlation function and also spectral function, and then they get this heavy momentum diffusion coefficient. And from this calculation, they get this kind of value, which is slightly smaller than our previous calculation. But now their value is very consistent with the other value from different calculation. Okay. Then now I also want to switch to my last topic, which is some also some modeling of the spectral function by using perturbation theory. But in this case, we didn't use color electric correlation function, but we really use our mesonic correlator itself, but using the same calculations. And that means our calculation has been done on the quenched QCD configurations, but very large on the very large lattice, and we also performed very precise continuum extrapolation. And first, we started this study for photoscalar channel, because photoscalar channel basically should not have any transport peak. So this is much simpler than the vector channel case. So first, we start with this, and basically what we did is to define our model spectral function like this, and our part of the so-called part of the spectral function is consists of two parts. One is just a vacuum asymptotics, which can be calculated from perturbation theory. So this corresponds to high energy part, and also some threshold around threshold part, which can be given by so-called PNRQC calculation. And also, this part should vanish around low energy region. So we also introduced some suppression term here. And of course, this since we cannot determine the precise enumeration constant, and also we didn't know the real didn't know the threshold value. So we, based on this perturbation perturbative function, we further determine our so-called model spectral function like this. We introduced scale factor here and some shift here, and these two plots shows our result, and this data points correspond to our lattice data, and this band just corresponds to this perturbative spectral function itself. And then we fit, this model spectral function to our last data, then we get this solid line. And as you can see, our model spectral function express our last data pretty well. And this is 1.1 TC and 1.3 TC. And also 1.5 TC and 2.5 TC. So all temperatures, at all temperatures, our particle spectral function describes our last data perfectly. And then these two plots show corresponding spectral functions. And these dashed lines correspond to this part of the spectral function itself, and these solid lines correspond to our model spectral function. And after modifying this scale factor and this shift. And as you can see, okay, so this left-hand side panel corresponds to charmonium, and right-hand side corresponds to botonium. And as you can see, for charmonium, basically you cannot see any band state, any resonance peak here. So that means to describe our lattice correlation function data, it is not necessary to have any resonance peak here. And also, but on the other hand, for bottom, one can see clear resonance peak structure here. So in that sense, for bottom, at least maybe, up to 1.5 TC, it is this resonant peak may be very present for bottom. Then we extended our study to the vector channel, and here we newly introduced this transport term here. So now our fitting parameters are A, B, and this transport part. And first we take this part as a constant. So just A, B, and this part are just constant, some parameters. And then these are our fitting results, and these circle symbols correspond to our last data, and these bands correspond to some fit result with constant, and this black curves correspond to the fit result without this constant. And as you can see, this constant is quite sufficient to describe our last data. And after introducing this transport term, our model spectral function successfully describe our lattice data like this at any temperature. Then finally, I will show our spectral function results, and it is quite similar to the pseudo-scalar case. That means this for charmonium case, one cannot see any peak structure here. But on the other hand, for bottom, one can see some peak structure at least up to 1.5 TC. That means any peak structure is necessary to describe our data, our last data for charm. But such kind of peak structure might be needed for bottom. Then finally, we also try to get the diffusion coefficient itself from the transport part. And this time we fix this A and B from this calculation, and we just we just introduce this kind of ansatz for transport part, and we changed this D value from 1 to 9 in the sense of 2 by TD. And then we get this kind of result. And so what we found is that basically there is not so large D dependence here, except for some small value of D. I mean, so basically this is no transport peak data, but as you can see, this pink curve might deviate from our Lattice data also. That means there might be some lower bound of this diffusion coefficient. That might be 2 or something. So this, at least this one cannot describe 2 pi TD equal to 1. It cannot describe some data, some Lattice data here. But anyway, maybe we need further check to confirm this kind of calculation. Okay, so let me summarize my talk. So heavy quarks are very important approach to investigate quark-gluon plasma, and especially the spectral functions contain all information about the immediate properties of heavy quarks. So it is very important to investigate spectral functions from theory side or maybe from Lattice calculations. But unfortunately, there are some difficulties to study the spectral function on the Lattice, but there are a couple of approaches to overcome these difficulties. And there are a lot of results for the spectral functions already. And but there are a lot of still open questions, and maybe some for example, melting temperature or something, or diffusion coefficients are not still precisely determined, or maybe not conclusive. So maybe one should further, or maybe one has to further study this spectral function, and maybe one need more precise calculation to get more precise value of melting temperature and diffusion coefficients. And yeah. Okay, so that's all. That's all. Thank you very much.
Thanks, Hiroshi-san, for this comprehensive talk. And so we open the session for questions. Okay, so I had a couple of questions for you. So is it possible? So there are two issues here. Firstly, you have to first take the continuum limit of the correlators for the heavy quarks, and then you have to do the Fourier transform of it. So in all the studies that you showed, many of them, the continuum limit is not yet taken, right? Because you're working on a very fine lattice, but I guess, so is it possible to use like gradient flow methods to take the like vector current correlators for heavy quarks, and then try to get the continuum value, continuum limit for these correlators, or the the correlators using gradient
Yeah, I
flow,
think that
or is there a
that is possible, and maybe to get maybe better signal for the correlation function is quite helpful to get more precise extraction of the spectral function. So maybe that's a very interesting thing. And
so,
and as I said, there has been already some study for in that direction, like this kind of stuff. So they have already done some gradient flow analysis for calculation of the heavy momentum at least.
but this calculation is for the pure gauge theory with this
Right. Yeah,
electric
right.
field
This is clear.
insertions, right?
Yeah, yeah.
Is it possible also to extend using like the vector current correlators, or looking at the pseudoscalar current correlators with the heavy quarks,
I think it is possible, but yeah.
and then take do a gradient flow for that?
Hmm. Yeah, maybe I think there's no problem, and maybe I can. I mean,
And regarding your this slide, slide number 26. So this so what is the statement here? So when you varied this 2 pi times this diffusion constant in terms of the temperature, when it is 1, then you see a significant deviation of these correlators. But
yeah,
from
of course.
2 and beyond, all the ansatz, they fall on top of each other and also to the lattice point.
Yeah,
Is
this is
it
quite.
correct interpretation of this?
Yes, yes, but this is quite maybe complicated program because at least maybe one should have some sort of transport structure here, but the problem is that since our lattice data is not precise enough, maybe one can change, and if do some sort of I mean Bayesian analysis of something to get spectral function, then one can get some sort of spectral function by changing. If you change this transport part, then maybe at the same time maybe some bulk part can drastically change, and that there's some complicated maybe cancellation or something. So if you have enough good enough quality of data, then maybe that kind of uncertainty can be I mean uh, can vanish at some point. But unfortunately, our lattice data is not so precise enough. Then still our spectral function is not so stable. So maybe that is so from this result, maybe one can uh, at least I can get some such kind of impression. I mean, one can have any value of the transport, uh, 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 any shape of transport peak, but that is not true, right? And so maybe this is just coming from our poor data. I mean, quality. So at some point, maybe one, but if you,
But the errors are already within 10%, right? Sorry.
there are, yes, yeah,
You see, the errors are already within 10%. So how much do you need to further reduce the errors to get a much more uh, quantitative estimate?
that is a good question. But yeah, at some point I have estimated the contribution of the transport part to the entire operation function, and I actually I found that that is quite small. So in that sense, maybe this error is still too large to get precisely to extract precise information about such small contribution. So yeah, I don't remember the value, but
Okay, thanks. And are there any further questions? Okay, I don't see any at the present moment. So, of course, you can always write the questions if it comes later in the chat box, and we can discuss later or forward it to him so that he can directly answer to the participants. So thanks again, Hiroshi-san, for the wonderful talk, and thanks for coming. And we also thank Masakio and for his talk. And we close the session here now, and we reconvene after 50 minutes.
thank you.
Thank you.